In this video, I am going to give you some problems that come from chapter 2.1, 2.2, and 2.6. Those are the linear differential equations with integrating factors, separable equations, and exact equations. But I kind of mix them up and I don't tell you what kind of equation it is, so you'll have to choose which technique to use. I do have other topics that I had listed because originally I was going to be really ambitious and put in a few more problems, but I think at this point I'm not going to have time to do that. I need to get going with chapter 3. But these are the other topics I did want to mention for numerical methods. Euler and Picard, they are both numerical methods for solving differential equations. Euler is a much more practical one and often is programmed in computers. This one here is not as efficient computationally, so it's often not used for computers, but it's really good for doing proofs, which is why we learned how to do it, so we could prove existence and uniqueness. A couple of things about population growth and also mixtures. The equilibrium solutions, as you have seen, become very important because we want to know how populations settle out, how mixture concentrations settle out, and also these graphs. The qualitative graphs are also very important. Of course, all of these topics are important. These two are often optional topics at different schools. Okay, so as I said, this video only has part 1, or the problems from these three sections. And one last note, just because I prioritize these problems, don't think these are not important. You know, more than half the class are different applications in how to use these differential equations. The only reason why I chose to separate this out is because, you know, these are fairly straightforward, the modeling, whereas the 3 topics should really be covered together or have some problems that are together. First, we're going to address problems: linear equations with integrating factors, separable equations, and exact equations, possibly with integrating factors. And the idea is that you'll be given a problem and you need to figure which of these approaches you want to use. If you have a differential equation and you're trying to determine what technique to use, the first thing I would do is I would look to see if it's linear. So, in other words, I'm looking to see that this y is by itself. It's not raised to any power. It's not a function of something else like either the y or sine of y. So if it is linear, you can either solve it directly. In other words, you can see that this is the derivative of some function, then you can just integrate both sides directly, or you can use this integrating factor mu of t is equal to e raised to the integral of p of t, this function that multiplies y, d of t. And you remember that mu of t was chosen so that the derivative of mu of t y of t with respect to t is equal to mu of t dy dt plus mu prime of t y of t. Otherwise, we try to put it in this form, mxy plus nxy dy dx equals 0 form. Now, you try to see then if you can get m of x only dependent m of xy only dependent on x. You know, if there's a y term here, maybe you could divide everything by y or something. But you attempt to get it in this form where m of x is only dependent on x, and the function that multiplies dy dx is only dependent on y. And if you can do that, you have a separable differential equation. You can separate the x and y variables, and then you can integrate. And you want to remember that y is a function of x, which for that reason, I often write y as y of x. Otherwise, if you cannot get it into this form where m of xy is only dependent of x and n of xy is only dependent on y, then you look to see if you have an exact differential equation. And you do that by looking if the partial derivative of m with respect to y equals the partial derivative of n with respect to x. And if it is, then your solution is going to look like the integral of mxy dx, and that will plus a function of y. So c of x, your solution is equal to q of xy, that's the integral, plus a function of hy. And hy is going to be the integral of n of xy minus this part of your solution with derivative with respect to y, the whole integral with respect to y. And if this is not exact here, you can try an integrating factor using this equation here. Here I have 1, 2, 3, 4, 5 problems, and I've asked you to solve the differential equations without telling you where they came from. These three came from, one of them came from 2.1, one came from 2.2, and one came from 2.6. I just chose problem number 9 from each of those 3 chapters, and these 2 I won't tell you which, they just came randomly. So give the problems a try, and then I'll outline the solutions in the next slides. This equation is pretty straightforward, not linear because of this y squared. The next thing is whether or not it's a separable equation. So I rewrote this so that I sort of have this mxy form plus some nxy times y prime form equals 0. You might be tempted to say, because this mxy plus nxy y prime form equals 0, that this m here is dependent on both x and y, and therefore it is not separable. However, it's not that you just naturally can write it as whether or not you can write it as mx. It's whether or not you can get it into this form to determine if it's separable. So I can by dividing everything by y squared. And now you see I have an equation where I have m only dependent on x, and I have an n of y only dependent on y. So I have a separable equation. You can see how I separate and finish this solution. In this equation, you can see that our variable y is definitely linear. So it's a linear equation, and here I don't immediately see, you might see how to integrate, but I didn't, so I needed an integrating factor. And then you can see how I finished this problem here. From this equation, you can see this problem is not linear because of this y times this dy dx. And you can also see it's not separable. This is definitely where I have an mx y. It's not dependent only on x. And here I have an nxy, specifically, I have an nxy that also I just can't get rid of the x term. It has to be dependent on x and y. So is it exact? So I can take the partial derivative of m with respect to y, and I get -1. I can take the partial derivative of n with respect to x, and I get -1. So I find it is exact. So I use my equations for exact equations, and you can see my solution here. On this problem, I was tricked. I took this problem out of, this is problem 19, out of section 2.6, the one that's supposed to be about exact equation, but actually it's a linear equation. I suppose you can solve it as if it were an exact equation, but that's like way overkill. It's much easier as a linear equation. You can see how I solved it here. And what I was really after on my last problem, the one I told you that I was tricked, I wanted to find an exact equation that needed an integrating factor. So one, you can see that it's not linear. These y squareds, y cubes all over the place, it's a problem. Then my m of xy, there's no way I can get rid of this. The y's in here, they're there to stay. So m of xy is here, n of xy is here. Again, they're not separable because m of xy depends on x and y, and n of xy depends on x and y. I take the derivative of m with respect to y. It is not equal to the derivative of n with respect to x, so it is not exact. So I tried an integrating factor to make it exact. I used my formula, and I found my integrating factor is e to the 3x, so I multiplied my entire equation by e to the 3x. I looked again now at my new equation. I can find that it is exact. So continued on the next slide. So I summarized everything here. Here's my integrating factor. Here's my new equation when I multiplied everything by my integrating factor. And then here I found that it was exact. So now I went ahead to try to find my solution and I used my formula with the integral of m of xy dx. I got this equation here, and I was looking at it, and it looked kind of difficult. So I thought, well, maybe instead of using m of xy dx, I could use n of xy dy. So here I have my c of xy dy is equal to n of xy dy. I wrote that out, and I got my solution plus, since this is an integral, it's this plus some function of x. And then similarly, my h of x, now I take my m of xy minus dq here with respect to x. And then I get 0. You can see h is equal to c, and then I have my solution here. So this is sort of an interesting thing that I had not mentioned before in my videos, but this is kind of an interesting trick. If you don't like taking this integral, you can switch over to this integral, but you just have to remember now everything's with respect to y, and then your extra function here is with respect to x. And that's it for this video. Thank you for watching.